For years, the standard explanation for Mars was almost too neat. It once tried to follow Earth's path, couldn't manage it, dried up, and became the lifeless red desert we see today. New research from 2025 and 2026 is now unraveling that explanation, and what's replacing it is far more unusual. The latest major development arrived on June 26, 2026, when Oxford University scientists published work in Nature Astronomy using seismic recordings from NASA's InSight lander. About 24 kilometers under the Martian surface, they found a hidden layer where seismic waves changed speed and direction in a way that pointed to a shift in rock composition. A thick band of dense, old ultramafic rock. Further down, near 38 kilometers, lies the true boundary separating crust from mantle. Between these 2 points sits a 14-kilometer zone of cooled, mineral-rich rock, something that shouldn't exist if Mars's geology were as simple as long believed. The study's lead scientist explained that this points to Mars once running huge, long-lasting systems of molten rock that reshaped and redistributed material throughout its crust over enormous time spans. A mechanism called transcrustal magmatism. Until this discovery, that process had only ever been documented on Earth, where it depends on plate tectonics, the slow grinding motion of Earth's crustal plates that continuously feeds new magma upward and recycles material through the crust. Mars has no such plate movement. It never has. Yet the evidence shows it somehow developed a comparably sophisticated internal magma network anyway. What makes this even more remarkable is its apparent reach. This isn't an isolated pocket beneath the InSight site. Satellite data has picked up the same depth signature spread across much of Mars's northern hemisphere, suggesting a linked web of massive magma chambers that could have stayed active across huge portions of the planet for billions of years, rather than being confined to a single volcanic hotspot. Oxford researchers noted that this kind of ongoing geological recycling is strongly tied to how planets end up with atmospheres, oceans, and the raw conditions needed for life. On Earth, that recycling helps stabilize climate and keeps water and other key elements moving through the system over long timescales. Scientists had generally treated plate tectonics as essential to building that kind of life-supporting engine. This finding challenges that assumption directly. It shows a planet can develop intricate geology, complex chemistry, and habitability-related conditions without any plate tectonics at all. That one insight quietly changes how astronomers think about which distant worlds might be capable of supporting life, since it widens the range of planets worth considering. It also sets up everything else researchers have since uncovered about Mars's hidden interior, because a world with billions of years of internal heat is a world that could have kept water alive somewhere unexpected. Alongside the magma discovery sits a separate, arguably even more striking finding NASA revealed in September 2025, something the agency described as one of the most important results in the history of Mars exploration. It centers on the Perseverance rover, exploring Jezero crater since it landed there in February 2021. During its survey, the team noticed a reddish, striped rock about a meter across, given the nickname of a waterfall from the Grand Canyon. At first glance, it looked unremarkable. Once Perseverance's instruments examined it closely, everything changed. Scattered across the rock's middle band were small, irregular, light-colored patches, each bordered by a thin, dark rim, nicknamed leopard spots. Testing revealed the spots consisted of two particular minerals, a water-bearing iron phosphate and an iron sulfide, arranged not randomly, but in a structured, repeating layout. NASA's peer-reviewed paper described these leopard spots as chemical reaction fronts, zones where ancient oxidation-reduction chemistry occurred. On Earth, those same reaction types are frequently the result of microbial processes rather than plain geology. The iron phosphate mineral typically forms where organic matter is decomposing, while the iron sulfide is often produced by microbes that draw energy from sulfate. Finding both minerals arranged in tight, repeating, concentric patterns at a microscopic level matches what planetary scientists call a biosignature, a chemical footprint left by living organisms. Nicola Fox, then heading NASA's Science Mission Directorate, said publicly that this was the nearest the agency had ever come to finding evidence of ancient Martian life. Coming from someone in that role, this amounts to saying that a rock already sampled by Perseverance shows patterns more closely resembling ancient microbial activity than anything seen before. To be fair, NASA has stopped short of calling it proof. It's labeled a possible biosignature, and researchers have worked hard to rule out non-biological causes, testing geological, chemical, and heat-based explanations. A follow-up paper in Nature, published September 2025, found that none of the purely geological theories held up well. Every non-biological explanation ran into serious issues, while the biological explanation, though still unproven, fit the evidence best. Then, in June 2026, another piece surfaced. A study in Science Advances confirmed that rocks in the nearby Bright Angel Formation, close to the leopard spot location, contain macromolecular carbon, large, complex carbon atom structures. On Earth, this kind of carbon typically shows up in rocks holding fossilized biological material or inside meteorites. The team called it unambiguous confirmation of organic compounds on Mars. And notably, these weren't spread randomly. They clustered in rocks from an ancient lake bed, within clay layers that form only where water once existed, right beside the leopard spot rock. Combine the magma findings with the leopard spot organics, and a coherent picture emerges. An ancient lake, water-formed clay, complex organic carbon, and mineral patterns tied on Earth to microbial chemistry, all clustered together, sitting above a subsurface once laced with active magmatic heat. The piece that links it all, though, didn't come from studying rocks. It came from listening to Mars tremble. In 2024, a team analyzing seismic readings from NASA's InSight mission produced a result that caught planetary scientists off guard. Somewhere between about 7 and 12 miles below the Martian surface, seismic waves slowed in a way that matched liquid water sitting inside porous rock, essentially an aquifer, similar to those found on Earth. The volume involved is enormous. Spread across the entire planet's surface evenly, it would form a global ocean somewhere between half a mile and over a mile deep. Separate teams at the Australian National University and the Chinese Academy of Sciences later backed up this conclusion using a different seismic data set, strengthening the case. Then, in March 2026, NYU Abu Dhabi researchers published findings showing that ancient sand dunes in Gale Crater had been cemented by groundwater flowing through them, long after Mars's surface lakes and rivers had already vanished. This means the underground water system stayed active for far longer than expected. Taken together, these results suggest Mars's story isn't simply it dried up and died. Instead, its water relocated. As the surface cooled and the thinning atmosphere could no longer support liquid water above ground, billions of years' worth of accumulated water is believed to have gradually seeped downward through cracks in the crust. Fractures produced by the intense meteor impacts Mars endured early in its existence. Deep enough underground, leftover geothermal warmth kept that water in liquid form. Seismic evidence suggests a meaningful portion may remain liquid even now, resting in a huge, dark, mostly unexplored reservoir miles beneath the surface. This carries real weight for astrobiology. On Earth, microbes have been discovered living in cracked rock more than 2 kilometers underground, in complete darkness, under extreme pressure, entirely cut off from sunlight and surface ecosystems. First found in South African gold mines, these organisms survive on hydrogen generated when natural radiation splits water molecules apart, a process known as radiolysis, allowing them to persist for extremely long periods in total isolation. If Mars holds a similarly vast underground aquifer, and if the surrounding rock contains radioactive elements, which sampled Martian rocks confirm it does, then the same basic chemistry supporting deep life on Earth could plausibly exist on Mars today, not merely in its distant past. NASA researchers have said this discovery effectively redirects the hunt for Martian life away from the surface and toward the deep subsurface, since the surface itself is exposed to intense radiation, drastic temperature swings, and has no liquid water or protective shielding at all. To understand why Mars's water ended up hidden underground, it helps to look at its core. Structurally, Mars isn't so different from Earth. It has a solid inner core wrapped in a liquid metallic outer core. On Earth, movement within that liquid layer generates our planet's magnetic field. Mars once had this same setup, and billions of years ago, it too had a working magnetic shield. The key difference is that Mars's outer core eventually slowed down too much to keep generating that field. When its internal dynamo stopped, the shield it once produced faded away with it. Without magnetic protection to deflect solar radiation and charged particles, Mars's atmosphere gradually escaped into space. As atmospheric pressure dropped, the conditions required to keep water liquid disappeared, and whatever surface water remained either evaporated or froze. Here's where the story connects. While Mars still had its magnetic field, it also had a denser atmosphere and enough surface pressure to sustain liquid water. Evidence of that earlier, wetter version of Mars is visible everywhere. Dry riverbeds, sediment from vanished lakes, and massive channels clearly shaped by catastrophic flooding. Jezero Crater, where Perseverance operates today, was once a lake fed by rivers flowing into it. During that period, Mars had water on its surface, heat from active volcanic systems. the same transcrustal magmatic network identified by the 2026 Oxford study, an ongoing geological activity generating fresh minerals and chemical energy sources. It also had a magnetic field keeping radiation at tolerable levels. By nearly every scientific standard used to assess habitability, early Mars met the criteria. Not partially, not arguably. According to planetary science definitions, it was genuinely habitable. Adding another twist, Perseverance's laser instruments recently detected tiny grains of corundum in pale rocks within Jezero crater, the same mineral behind rubies and sapphires on Earth. Presented at the 2026 Lunar and Planetary Science Conference, the discovery mattered not for its value, but for what it implies about the rock's formation. Corundum needs very particular chemical conditions: high aluminum, very low silicon, usually forming under intense heat or through tectonic activity. Mars isn't expected to easily produce either scenario, yet the mineral was confirmed there through spectroscopy, another sign that the planet's geological past is stranger than models predicted. Step back, and the collection of discoveries forms a pattern that's difficult to dismiss. Mars appears to have run an interconnected network of magma reservoirs through its crust for potentially billions of years, something previously believed to be unique to Earth. It once had water flowing across its surface, filling lakes and craters such as Jezero. Its internal layout, a solid inner core inside a liquid outer core, closely resembles Earth's structure. Current seismic evidence points to a massive underground aquifer several miles down, potentially large enough to blanket the entire planet in an ocean up to a mile deep. Layered on top of the geology is the chemistry. Perseverance uncovered a rock displaying mineral patterns that, on Earth, are strongly linked to microbial activity, and scientists haven't found a purely geological explanation that fits as convincingly as the biological one. Right beside that rock, researchers confirmed complex organic carbon, the same type found on Earth either in fossil-bearing rock or meteorites. Rather than scattered randomly, both discoveries sit within the same ancient lake bed, inside clay layers that could only form where water once existed. None of this confirms Mars ever hosted life, and no serious scientist claims otherwise. But the old narrative, a planet that attempted and failed to mirror Earth, too small to hold an atmosphere and too geologically plain to develop meaningful chemistry, no longer fits what's been found. What the recent research actually shows is a planet that achieved Earth-level geological complexity without Earth's usual mechanisms, and one that didn't lose its water, so much as move it, storing a massive reservoir underground that may still be present today. That shifts the central question researchers are asking. It's no longer, could Mars have supported life at some point? That's largely resolved. It could, and did, meet the conditions. The real question now is whether whatever chemical or biological activity began there billions of years ago ever truly ended, or whether it simply withdrew along with the water, moving from a warm, wet surface into a cold, dark, chemically active hideout deep below ground, isolated from the outside universe for an immense stretch of time. For now, that question stays unanswered, and the reason is more about engineering than science. Drilling 7 to 12 miles into Martian rock is far beyond what current technology allows. No existing or near-future mission has the capability to reach the suspected aquifer's depth. Whatever answers exist, they remain out of reach for the time being. Closer to the surface, funding presents its own obstacle. The Mars Sample Return mission, meant to bring Perseverance's collected rock samples, including the leopard spot rock, back to Earth for detailed lab analysis, is under serious financial strain, and its future is uncertain. Without it, the clearest answers about whether those minerals and organic compounds have biological origins may stay locked away in samples already collected but never returned. Meanwhile, China's Tianwen-3 sample return mission is aimed at a different site later this decade, one seen as less geologically compelling than Jezero. So the raw evidence needed to answer one of humanity's oldest questions already exists. It's sitting inside rock cores drilled by a rover currently stationed in an ancient lake bed, and within a hidden reservoir several miles beneath a rust-toned desert roughly 140 million miles from Earth. What's missing isn't the evidence itself. It's the means to access it and bring it home. Look at how much has unfolded in just the past year. In September 2025, NASA's science lead publicly described the leopard spot rock as the closest the agency had come to detecting ancient life. Not long after, a peer-reviewed study confirmed Mars's solid inner core, ending a long-standing debate over the planet's deep structure. Early 2026 brought confirmation that groundwater was still moving beneath Gale Crater long after surface lakes disappeared. March 2026 extended the estimated timeline for how long that underground water stayed active. and June 2026 delivered two major results together: confirmed organic carbon near the leopard spot site, and the Oxford team's discovery of an ancient, Earth-like magma network spanning much of the northern hemisphere. Any single one of these findings would normally count as a major scientific milestone. 6 landing within 1 year, all pointing at the same planet and the same underlying possibility, is a different category of event altogether. If samples like the leopard spot rock are ever brought back and confirmed to contain genuine fossil evidence, or if the underground aquifer is eventually reached and found to hold microbial life, the consequences would extend well beyond planetary science, touching how common life might be throughout the universe, and offering one of the most significant clues yet toward understanding why, in a universe, this large and old, clear evidence of others has remained so elusive.